Okay, yeah, let's start. So today we will talking about a new chapter on PBRT, which is light sources. So in order for object in a scene to be visible, there must be like source of illumination or some light. And this chapter presents a light interface, which is a bunch of different light sources, and then it implements a number of useful light sources, and the light transport routines can generally operate without knowing which particular type of lights are in the scene. Yeah. Wide variety of light source models are introduced in this chapter. The variety is slightly limited by PBRT's physically based design. Like many non-physical light source models have been developed for graphics, incorporating control over a property like the rate at which light falls off with distance, which objects are illuminated by the light, which object casts shadow from the light, and so on. This is incompatible with the physically based light transport algorithms and thus cannot be provided in the models here. Yeah, as an example, consider a light that does not cast shadows. Yeah, that's just like adding more object will increase the energy, which adding each added shells increase the total received energy, which directly violates the principle of the energy conservation. Yeah. In scene with many lights, it's impractical to account for the illumination from all of them at each point being shaded. So yeah, fortunately this issue is yet another can be handled stochastically via Monte Carlo method. Given a suitable weighting factor and unbiased estimation of the effect of illuminating from all the lights can be computed by considering just a few of them or even just one. This was a topic of that blog post we just talked about recently. And yeah, the last section of this chapter introduced light sampler, which define interface for choose such a light source as well as number of implementations of it. So today we will just talk about the simple stuff, the interface of light. And there are totally 9 implementations. Because point light is also not physical, but I guess it's just something we can simulate in PBRT. All light must be able to return their total emitted power phi, among other things. Yeah, this makes it possible to sample light according to the relative powers as weight, basically. Yeah, devoting more sample to lights that make largest contribution can significantly improve rendering efficiency. Light interface does not completely abstract away all the differences among different types of light sources. While doing so would be desirable in principle, in practice, PBRT's integrators sometimes need to handle different types of light source differently. both for efficiency and for correctness. Yeah, we have already seen an example in the random walk integrator. I think random walk is basically like naive path tracing without any kind of explicit light sampling. Yeah, but yeah, even in there, the infinite lights receives special handling because they must be considered for ray that escape the same without hitting any geometry. Yeah, this infinite light is basically the background. Another example is that the Monte Carlo algorithm that sample illumination from light source need to be aware of which light are described by delta distribution, since this affects some of their computation. Oh yeah, I think this is for like specular light, like mirrors, something like that. So yeah, for type of light, delta position, light that emits solely from a single point of space. Oh, sorry, ignore what I said here. Yeah, okay. Anyway, delta position, light that emits solely from a single point in space. Delta here referred to light can be described by direct delta distribution. Oh, because it's like infinitely small. That's why it's a direct delta distribution. Is that why? And the directional light and area light and infinity. And then this delta light basically check if these two categories that need some special handling. Be able to sample direction at a point where illumination may be incident is an important sampling operation for rendering. Consider the diffuse surface illuminated by a small sphere area light source. Sampling direction using the BSDF sampling distribution is likely to be very efficient because the light is only visible within a small cone of directions from the point. Yeah. A much better approach is to instead use a sampling distribution that is based on the light source. Yeah, in this case, the sampling routine should choose from among only those directions where the sphere is potentially visible. So this important task is the responsibility of implementation of the sample method. Color passed a light sample context that provide information about reference points in the scene, and And the light optionally returns light sample that encapsulates incident radiance, information about where it is being emitted from, and the PDF value of the sample point. If it is impossible for light to reach the reference point, or if it is no valid light sample associated with the point, then an invalid sample can be returned. What do I mean by invalid sample? It's just like null, or do it return something special? I don't know. Allowing complete PDF indicate whether the sampling routine may skip generating samples for directions where the light contribution is small. This capability is used by integrators that apply MIS. So MIS composition, multiple important sampling. Light sampling context takes the usual role of encapsulating just as much information about point receiving illumination as the various sampling routine used. So it has a point at normal, the point and the thing, and the surface normal and the shading normal. Oh yeah, that's PBRT's like error bound stuff that I don't really understand. But anyway, they have some special error bound types. Some of the following sampling routine will need this information as part of their sampling process. If the point is in a scattering medium and not on a surface, the two normals are left as 0. The context does not include a time. PBRT's light source does not support animated transformations. As with other context class, a variety of constructors make it easy to create a light sample context. And convenient method just convert this error bound point to a normal point. So the sample method returns the incidence radiance from the light at the point, and also returns the direction vector omega that given the direction from which radiance is arriving. Light samples are bundled up into instances of the light sample struct. The radiance L is the amount of radiance leaving the light toward the receiving point. Does not include the effect of extinction due to participating media or occlusion if there is an object between the light and the receiver. Yeah, that's not a job of light sampling, I guess. Omega I gives the direction along which light arrives at a point. That was specified via light sample context. Yeah, omega I is this, right? Finally, the PDF value, yeah, it's the PDF value used for important sampling. This PDF should be measured with respect to solid angle at the receiving point. Just as we saw for perfect specular reflection and transmission with BSDFs, light sources that are defined in terms of delta distributions fit naturally into the sampling framework. Although they require care on the part of the routines that call their sampling method, since there are implicit delta distribution in the radiance and PDF value that they return. For the most part, this delta distribution naturally cancel out when estimators are evaluated, although MIS code must be aware of the case. Just as with BSDFs, for samples taken from the delta distribution, like the PDF value in the returned sample should be set to 1. Yeah, otherwise it's either 0 or infinity, which is not that useful, but they just set it to 1. Yeah, I think this is parallel to how they deal with BSDF for the perfect specular BSDF. Related to this PDF method just returns the PDF of the sampling given direction omega I from the point represented by context. This method is particularly useful in the context of MIS, where the BSDF may have sampled direction and we need to compute the PDF for the light sampling that direction in order to compute the MIS weight. Implementation of this method may assume that a ray from context in direction omega I has already been found to intersect the light source. And as with sample L, the PDF should be measured with respect to solid angle. Yes. It's just to less information, to less work than this one. Yeah, just calculating the PDF basically. Here the returned PDF value should be 0 if the light is described by direct delta distribution. If a ray happens to intersect an area light source, it is necessary to find the radiance that it emits back along the ray. This task is handled by the L method, which takes the local information about the intersection point and the outgoing direction. This method should never be called for any light that does not have geometry associated with it. Another interface method that only applies to some type of light is LE. To enable infinite area light to contribute radiance to rays that does not hit any geometry in the scene. Yeah, okay. And finally, pre-process method. Take a rendering scene bond as a rule. Some light sources need to know this bond, and they are not available when lights are initially created. Three additional light interface methods that will be defined later, closer to the code that use them. Bond that provides information about the light spatial and directional emission distribution. Use them to create acceleration hierarchies for light sampling. Interesting. And sample LE and PDF LE also for infinite light. Yeah. They are cornerstones for bidirectional light transport algorithms. Photometric light specification. Yeah, PBRT uses radiometry. Yeah, however, light sources are often described in photometric units like lumens rather than joules. Yeah. One advantage of photometric descriptions of light emission is that they also account for variation of human visual response with wavelengths. Therefore, light source in PBRT scene description file can be specified in terms of luminous power that they emit. These specifications are then converted to radiometric quantities in code. Okay. And light base class. Just some common stuff in it. It is not required that light in PBRT inherit from light base, but light must provide the implementation of film or light method if they do not. So light have a type. Render from light. Okay, so it's a transformation matrix, I think. From the light coordinate space to the rendering space. Participating medium on the inside and outside of the light source. Also provide default implementation of L and LE so that light that do not respectively area or infinite light do not need to implement these themselves. Let's return 0. Most of the light implementation take a spectrum value in their constructor to specify light spectrum emission, but then convert it to a densely sampled spectrum to store it in a member variable. So yeah, they enjoy some efficiency boost. I am still a bit confused about how PBRT do this spectrum rendering stuff, but I guess it's just because it's a bit over my head. Yeah, need to reread those and also the spectrum rendering blog posts. Yeah, anyway. A densely sampled spectrum that covers the visible wavelengths use approximately 2 kilobytes of storage. For scenes with millions of light sources, the memory required can be significant. So, just another interaction, they have lookup spectrum that use the intern cache. Okay. And the detail of initialization of spectrum caching, including initial mutual exclusion if multiple threads have called the lookup spectrum concurrently. And use appropriate memory allocator. Yeah. Able to pass the provided allocator to the densely sampled spectrum constructor, which in turn ensure that it's used to allocate the storage needed for spectrum sample. Yeah, okay. Yeah, that's it for today. And we will not delve into like implementation detail of light sources, which will be later topic.